Hey guys, I'll be presenting the second part of the substructures. The first one is the retaining wall. These are relatively rigid walls used for soil laterally so that it can be retained at different levels on the two sides. Its purpose is to hold soil behind them. Retaining wall has design principles. The wall must be designed to ensure that overturning does not occur, sliding does not occur, the soil on which the wall rests is not overloaded, and the materials used in the construction are not overstressed. Retaining wall has factors that must take into account: the nature and type of soil, height of water tables, subsoil water movements, type of wall, and materials used in the construction of wall. Here are 6 types of retaining wall: mass retaining walls, cantilever walls, counterfort retaining walls, precast concrete retaining walls, precast concrete crib retaining walls, and reinforced masonry retaining walls. Mass retaining wall, a massive concrete wall that resists the overturning vertigo of its own weight. The mega tandem mass retaining wall block offers a versatile system with the natural look of stone, plus size and mechanical features enabling construction of walls up to 15 feet. These are sometimes called gravity walls and rely upon their own mass together with a friction on the underside of the base to overcome the tendency to slide or to overturn. They are generally economic only up to a height of 1.8 meters. Mass walls can be constructed of semi-engineering quality bricks bedded in a 1:3 cement mortar or of mass concrete. The latter could have some light fabric reinforcement to control surface cracking. Natural stone is suitable for small walls up to 1 meter high, but generally it is used as a facing material for walls over 1 meter. Cantilever walls are constructed of reinforced concrete. It consists of a relatively thin stem and a base slab. Cantilever walls are usually made of reinforced concrete and work in the principles of leverage. 2 basic forms can be considered: a base with a large heel so that the mass of earth above can be added to the mass of the wall for the design purposes, or if this form is not practicable, a cantilever wall with a large tube. Counterfort retaining walls. These walls can be constructed of reinforced pre-stressed concrete and are considered if the height is over 4.5 meters. The counterforts are triangular beams placed at the suitable centers behind the stem and above the base to enable the stem and base to act as slabs spanning horizontally over or under the counterforts. Figure shows a typical section and pattern of reinforcement for a counterfort retaining wall. If the counterforts are placed on the face of the stem, they are termed buttresses. and the whole arrangement is called a buttress retaining wall. The design and construction principles are similar in the two formats. So the next one is the precast concrete retaining walls. These walls are manufactured from high-grade precast concrete on the cantilever principle, usually to a 600 mm wide module. Well, the figure shown is an example of a precast concrete retaining walls. They can be erected on a foundation as a permanent retaining wall, or be freestanding to act as a dividing wall between the heaped materials such as aggregates for concrete. In the latter situation, they can increase by approximately 3 times the storage volume for any given area. Here's the other advantage. It's a reduction in time by eliminating the curing period that is required for in situ walls and eliminating the need for costly formwork together with the time required to erect and dismantle the temporary forms. The units are reinforced on both faces to meet all forms of steam loading. Lifting holes are provided, which can be utilized as trap fixing holes if required. Special units to form internal angles, external angles, junctions, and curve walls are also available to provide flexible layout arrangements. We also have the precast concrete crib retaining walls. Crib walls are designed on the principle of a mass retaining wall. They consist of a framework or crib of precast concrete or timber units within which the soil is retained. The figure here is an example of a precast concrete crib retaining walls. They are constructed with a face better of between 1:6 and 1:8, unless the height is less than the width of the crib ties, in which case the face can be constructed vertical. Subsoil drainage is not required because the open face provides for adequate drainage. So the last one is the reinforced masonry retaining walls. Steel reinforcement may be used in brick retaining walls to resist tensile forces and to prevent the effects of shear. Where the appearance is not important or the wall is to receive a surface treatment, reinforcement and in situ concrete within hollow concrete blockwork provide for economical and functional construction. This figure shows the application of standard profile, hollow, dense, concrete blocks laid in stretcher band as permanent formwork to continuous vertical columns. The height potential and slenderness ratio, or effective height to width for reinforced masonry walls, can be enhanced by post-tensioning the structure. For purpose of brick walls, there are a number of construction options. The first one is the gutta band with steel bars and concrete in the voids. The next one is the stretcher banded wide cavity with reinforced steel bars coated for corrosion protection. And lastly is the solid wall of perforated bricks with continuous voids containing grouted steel reinforcement bars. Since the most commonly used retaining wall is the L shape, I'll be showing you here the logic that will best explain why and where to put or to point the L shape of the retaining walls.
Retaining walls serve the important role of holding back soil and rock, just as dams hold back water. The first video in this series showed that granular materials such as soil and rock generate horizontal pressures that increase linearly with depth. Retaining walls must resist these pressures, and many strategies exist for doing so. In this video, we focus on the popular L-shaped cantilever design. If you were going to use an L-shaped wall to hold back soil and rock, as represented by these marbles, would you point the bottom leg towards the marbles or away from them? Many people would say that the base of the L should face away from the marbles. They probably realize that it is hard to tip the wall over towards the left if the bottom leg points in that direction. In engineering, we call tipping like this overturning. If the bottom leg points the other way around, it is easy to make the wall overturn. So easy, in fact, that I can do it with just a puff of air. It looks like the case is closed. Or is it? Before we declare a final verdict, let's use the model to find out what happens when the bottom leg points to the left, away from the marbles. As we add marbles, we discovered that the horizontal forces they produce create yet another mode of failure, namely sliding of the wall, and this occurs when the marbles reach a depth of 3 centimeters. In the model, we can increase the friction between the retaining wall and the base by placing a rubber mat between them. You will have to do some extra reading if you want to find out how they achieve this end in the real world. As you can see, increasing the friction allows our model wall to support a noticeably greater depth of marbles, but it still eventually fails by overturning, in this case when the depth reaches 8 centimeters. Now let's turn the wall around, so its bottom leg points towards the right, the side where the marbles will be placed. We again use a rubber sheet to prevent sliding, and we add some marbles. As before, the marbles generate a horizontal force that depends on the marble depth. You might be surprised that this wall can hold back 11 centimeters of marbles before it overturns. Can you explain why the wall can resist a greater height of marbles when the bottom leg points towards them? Is there an additional force that comes into play? Recall that granular materials generate both horizontal and vertical pressures. When the bottom leg is oriented away from the marbles, overturning is resisted only by the weight of the wall itself, and so it overturns easily. When the bottom leg points towards the marbles, the vertical pressure from the marbles helps to keep the wall upright. The downward pressure also increases the friction between the bottom of the wall and the ground, thereby reducing the likelihood of sliding. When engineers design L-shaped retaining walls, they imagine them overturning about the point labeled Q. They first calculate how strongly the soil pressure will tend to make the wall rotate about Q. We call this tendency to tip an overturning moment, and we label it MO. Next, they figure out the stabilizing moment, MS, produced by the soil pushing downwards on the horizontal leg of the wall. Lastly, they make sure that the horizontal leg is long enough that the stabilizing moment is at least as large as the overturning moment. Then the retaining wall will be stable. You might be surprised to learn that L-shaped walls are seldom used as dams. The reason is that pressurized water at the bottom of the dam can seep under the base of the dam, and if it does, the resulting upward water pressure on the bottom of the dam can generate an additional moment and make the dam overturn.
The next part of the substructure is the basements. Basement story is the lower story of the building, with the floor at some point is more than 1.2 meters below the highest level of ground adjacent to the outside walls. This definition is given in the context of inhibiting the spread of fire within a building, and generally the fire resistance requirements for basements are more onerous than for the ground or upper stories in the same building. This section on basements is concerned only with basement stories that are below ground level. The structural walls of a basement below ground level are in fact retaining walls, which have to offer resistance to the soil and groundwater pressures, as well as assisting to transmit the superstructural loads to the foundations. It is possible to construct a basement free of superstructural loadings, but these techniques are beyond the scope of this book. Waterproofing. Apart from the structural design of the basement walls and floor, waterproofing presents the greatest problem in basement construction. So since soil naturally produce or transmit moisture, waterproofing is very vital in this construction. Building Regulation C2 requires such walls to be constructed so that they will not transmit moisture from the ground to the inside of the building or to any material used in the construction that would adversely be affected by moisture. Building Regulation C2 also impose similar conditions on the construction of floors. There are three basic methods of waterproofing: monolithic structures, drain cavities, and membranes. Monolithic structures. These are basement of dense reinforced concrete using impervious aggregates for the walls and floor to form the barrier to water penetration. Figure here is an example of monolithic structures. Great care must be taken with the design of the mix, the actual mixing and placing, together with careful selection and construction of the formwork if a satisfactory water barrier is to be achieved. Shrinkage cracking can be largely controlled by forming construction joints at regular intervals, as also shown in the figure. This joint should provide continuity of reinforcement, and by the incorporation of a PVC or rubber water bar, a barrier to the passage of water. Drain cavities is another method for waterproofing. This method provides an excellent barrier to moisture penetration of basements by allowing any moisture that has passed through the structural wall to drain down within cavity formed between the inner face of the structural wall and an inner non-load bearing wall. Here is an example of drain cavities waterproofing. This internal wall is built of a floor covering of special triangular precast concrete tiles, which allows the moisture from the cavity to flow away under the tiles to a sump, where it is discharged into a drainage system either by gravity or by pumping. Membranes is another method of waterproofing. A membrane is a relatively thin material placed on either the external or internal face of a basement wall or floor to provide a resistance to the passage of moisture to the inside of the basement. If the membrane is applied externally, protection is also given to the structural elements and the hydrostatic pressure will keep it firmly in place. But a reasonable working space must be allowed around the perimeter of the basement. This working space will entail extra excavation and subsequent backfilling after the membrane has been applied. If adequate protection is not given to the membrane, it can easily be damaged during the backfilling operation. An internally applied membrane gives no protection to the structural elements, and there is the danger that the membrane may be forced away from the surface, by which water pressure, unless it is adequately loaded. This loading codes will reduce the usable volume within the basement as shown in the first two figures. There are also materials that are suitable in forming the membranes. Suitable materials that can be used for forming this are fiber-reinforced bituminous field, polyethylene sheet, polyisobutyl plastic, epoxy resin compounds, bituminous compounds, and mastic asphalt. Also, more recent developments for impervious membrane applications include polymer-modified bitumen with polyester reinforcement. This is available as a styrene-butadiene-styrene or SBS or atactic polypropylene or AFP. One of the membranes used in membrane waterproofing is the mastic asphalt. It has main advantages among all the membrane used in this type of waterproofing. First is it is a thermoplastic material and can therefore be heated and reheated if necessary to make it pliable for molding with a hand float to any desired shape or contour. Next is it is durable. Bituminous materials have been used in the construction of buildings for over 5,000 years and have remained intact up to this date, as also shown by excavation in Babylonia. It is impervious to both water and water vapor, so meaning it is assured that with the use of this membrane, these substances couldn't pass through the said waterproofing. And it is non-toxic, vermin and rat-proof, and is odorless after laying. It is unaffected by sulfates in the soil, which if placed externally will greatly improve the durability of concrete structure. Insulation of basements. Basements in heated buildings require insulation against energy loss through the walls and floor. The contribution made by the surrounding subsoil is significant, but insufficient alone to satisfy current energy conservation measures. Thermal insulation should be at least equivalent to that specified for above-ground walls and floors. Application of insulation. We have here for existing construction and for new construction. For the existing construction, assuming major excavation work and rebuilding is not viable, existing basements can be considerably improved by applying rigid insulation to the walls and floor. Surface finishes can be provided by dry lining the walls with vapor check, plasterboard, and covering the wall or the floor with particle board and a vapor control underlay to minimize the risk of condensation. The next one is the new construction. It is a typical application of insulation as shown in the figure. The insulation selected is usually a closed-cell water-resistant extruded polystyrene of low thermal conductivity and high compressive strength. Here's the last part of the substructure. Trees' effect on foundations. Close proximity of trees to buildings can result in direct physical damage to foundations, drains, paths, drives by growth and expansion of root systems. With conventional strip foundations and those provided for pre-1950s dwellings, where the concrete was rarely placed deeper than 0.5 meter, it is advisable to maintain a distance at least equal to the mature tree height between building and tree. Some relaxation may be applied where tree species can be identified as having less water demand. Heave precautions. In addition to foundation depths exceeding soil movement zones, the areas closer to the surface must be provided with additional treatment. The figure here shows the precautionary treatment to foundations in shrinkable clay. Here, prior to concreting, the trench is prepared with a lining of low-density expanded polystyrene or other acceptable compressible material, along with an outer polythene sheet sleeving. The polystyrene is designed to absorb seasonal clay movement, and the polythene acts as a slip membrane, preventing soil adhesion to the foundation.
What impact can trees have on my house? Trees suck out moisture from deep below the surface and hence increase the occurrence of soils shrinking. So as the tree grows and the root system becomes larger, the tree has the ability to suck more and more moisture from the surrounding soils. Creating inconsistent soil conditions around the building can place stress on the house footings. As trees grow above the ground, so does their root system below the ground. Typically, the roots of the tree can extend as far or even beyond the tree height. So for example, a 10-meter tall tree may have roots that extend 15 meters from that tree. The simplest and most obvious way to avoid this problem is not to plant trees close to the house, but this sometimes is neither practical or possible. It is important then to ensure that the engineer designs your footings with consideration to existing trees or possible trees that may be planted in the future. A common question we hear is, "The tree outside my house is tiny. Do you really need to design the footings with that tree in mind?" Well, yes, because trees grow. That little sapling, within just a few years, will grow into a large tree that can have a disastrous impact on your home.